So today, the idea is to look at these spatially extended systems, and the way we're going to view them is that there is some lattice, discrete spatial lattice, that at every site of the lattice is some kind of dynamical system. So here I did what might be kind of a complicated case. Just imagine that I had our three first-order differential equations for the Cellular, and then there might be some sort of weak coupling to a neighboring Cellular. And then one of the, all sorts of questions here. Some sort of foundational. How do these ideas of dynamical systems apply to this? What's the state of such a system? Of course, that's always the first question. If I give you a new system, like, what's the state space? Well, here, the implication is this lattice goes on forever. So we know that the dynamical system at each site in this cartoon picture is a three-dimensional system. Continuous state spaces are three. But now, I have potentially an infinite number of these. So the state space is literally infinite dimensional, which at first blush you'd say, you just kind of throw up your hands. Obviously, you're not going to visualize things, you'd think, but there are actually some ways to start visualizing what's going on in infinite dimensions. So today what I want to do is give a hint of how some of these ideas of state space, dynamic, invariant sets, even bifurcations, give you some traction on a system like this, even if it's infinite dimensional, and even if the techniques we've used so far, which is letting us stick our heads inside the box and see the state space, where it's not possible, we can still gain some traction on this. There are more conventional approaches to this area called pattern formation theory. Some very nice applied math and math textbooks. The lecture today is mostly about kind of the phenomenology and what some of the issues are when you approach an infinite dimensional system from the perspective of dynamical systems, complementary to the more mathematical treatments that analyze instabilities quantitatively. Well, if this is our basic picture of a lattice of dynamical systems, let's step back a little bit and imagine there are all sorts of different kinds of systems you can invent. So partly you should be thinking, oh, I can just invent all sorts of things myself. So when we're looking at a spatially extended system, we have some kind of lattice. So space is represented somehow. We have some local state space, and we have choices for that. And then we also have some temporal dynamic, right? So I'm today just going to cover cellular automata and nonlinear map lattices, because they're a little bit familiar to us. The cellular automaton is characterized as being sort of simplest in this whole tableau of having the state at each site be discrete. In fact, I think I'm only going to show you binary state, local state, cellular automata, but it's still rich enough. The space is a discrete lattice, either, well, again, today I'll probably just show you a one-dimensional spatial lattice, but you could do 2, 3, and 4 dimensions if you want, it depends on it. And then time is also discrete, so the system updates itself. But these variables I can change. So if you just change the local state to be continuous by putting, say, a discrete time one-dimensional map, I still have discrete space lattice and discrete time, but now some continuous state space at each site. What I just showed you, the Cellular lattice, if you will, that was continuous time, discrete space, and continuous local state. And various classes you've run into these things called partial differential equations, and those correspond in this tableau to continuous local state, continuous space, and continuous time. A little bit of the message here is that there are aspects of these more complicated systems, oscillator chains and partial differential equations, that we can begin to understand with these simpler. Okay, so right before we come to a new topic, we have to roll up our sleeves and give some definitions to get started here, just so I have some vocabulary to talk about this new class of dynamical system. So we're going to have space represented as some lattice in some number of spatial dimensions, call that D. So the way we represent that is we have indices integer indices in some dimensional space. If d was equal to 1, the indices would just be integers. If d is equal to 2, what this means is the indices for the cells or sites have 2 integers in them. We think of the lattice as being populated, having cells at each site, indexed by site index I, and there's some local state. So at site I, there's some state x in some local state space M. So again, if it was a Rissler, that was R3, and then we had that cartoon picture I was a pair of integers indicating some point in a 2-dimensional discrete lattice. So this is just looking in at each site, but now, of course, the state of the system is the configuration of the entire lattice, the local state of each lattice. So we need to make a distinction here between the local states of the system and the global state, which is the entire spatial configuration. So it's called the global state, is the configuration of all the local states. Well, the notation gets kind of messy here, but anyway, what I mean by x vector, or sometimes I'll use s bold as a cellular automata, there's just some big list of the local states for each lattice site. Again, the state space is going to be, well, we still denote it the same way as we did before for the low-dimensional systems, but it's some cross product of the local state space, one for each lattice site. Dot dot here means big. Formally, what we do is we put the lattice as the exponent here to indicate this cross product. So again, when I say what's the current state of the spatial system, what I should be saying is what's the current global state or global configuration, and that's specifying the local state at every lattice site. And I'm kind of belaboring an obvious point here, but in fact shifting from what we think is going on locally to the global is very important to keep those 2 different levels of description distinct. So again, the state of the entire system is a point in this infinite dimensional space. And it's infinite dimensional if this lattice is infinite dimensional. Obviously, the simulations I'll show you have a finite lattice, effectively big enough that it behaves as if it were infinite dimensional. Now, what's different from what we've been doing before? Before, with regular old dynamical systems, we had a state space and we had states that behaved in time. So in a sense, in a formal sense, we had an index that was just time. So what's different now, when we have a space-time system, is we have 2 independent coordinates, space and time. Or, if you like, space-time, if you want to nod in the direction of Einstein. And the question is, what can we learn? Well, what I was just talking about is just the basic architecture. We also have to specify some equations of motion, some dynamic for this dynamical system. So usually when we say a system is spatial, there is some notion that of neighborhoodness, of local relationship between them. So what we're going to do here is define a neighborhood, denoted eta here, and what's the picture of the dynamic is one that's locally specified. So what we do is at each site I, the dynamic looks in some neighborhood here, the 2 nearest neighbors and itself. That is then input to this local function phi that tells this site I what its next value should be at time t+1. So this is the little phi is the local dynamic, and then we say, often we study kind of symmetric about site I. So the range of coupling are often called the radius r. So this neighborhood here would have a radius of 2. In other words, the site I, as when it's updating, it looks to its the states of its 2 nearest neighbors on either side and its own state. And then there's a deterministic function of that, a map, into the next value it should take. So the local dynamic is just the specification of maps neighborhoods to next site value. Now, the way the system actually behaves, we imagine that at each lattice site, at each time, that same phi is applied simultaneously. So that defines the global update. That's how the system actually evolves. So we have this global dynamic, which is in some sense entailed or induced by the little phi. But as the system goes forward in time, it updates the entire configuration of time t to 1 at time t plus 1. So the entire configuration here goes, at time t goes to another configuration of time t plus 1. And we make a notational distinction to talk about this mapping from bi-infinite configuration to a bi-infinite configuration. We have capital phi. That's the global dynamic. So little phi obviously induces capital phi, depends on it, but they're not the same thing. This is a mapping from an infinite dimensional space to an infinite dimensional space. Little phi maps neighborhoods, which is a finite dimensional space, whose dimension depends on R, to next site values. Okay, so if I actually want to write down the equations of motion, what I write down for the entire update is I take the current configuration, that's input to the global dynamic phi, and I get a new configuration. Now, at this point, you know, if you just took the abstract dynamical systems view, now I have a state space. I have states, these are points, and they get updated by some function. So we're kind of back to the same setting we had before, except now, when I point at a state in a state space, it actually has some internal structure to it. For example, there's a notion of site I being next to site I minus 1 and site I plus 1. There's some internal structure, which this sort of point view of a state of dynamical systems doesn't naturally take into account. Right? When we were looking at the Russell and Rand, I wasn't saying, oh, the x variable of the three-dimensional state spaces are next to y. It's also coupled to z. There wasn't a notion of this internal structure in the system. That's essentially induced by this underlying spatial lattice, and that's actually how we're going to make progress. In the spatially extended system, not all variables talk to all other variables. They only talk locally, and that's going to lead to certain kinds of organization, structural organization, or pattern formation. So we could, sorry, yeah.
Just really quickly, do the dynamics in general depend on time or just the state? So at the low point, does it only depend on the states next to it, or maybe the time as well?
In this case, just the states. So just previous state, there's some mapping, which is function here, that takes us to a new state. No time dependence. Now the configurations, actual config, are going to change in time. But that's just like in the Russell case, the states were changing over time. But there was no, I wasn't modulating the vector field there, that was time independent right-hand side. And then we have two versions. Again, this is just what I've been saying, it's just introducing some vocabulary, sort of the basic architecture of these spatially extended systems. And we can have two different versions. One is discrete time map, or we could imagine also having continuous time systems too. I'm trying to describe what's common across all those different examples in that matrix we had before.
Hey, Jim.
Yeah.
So I've seen in other sort of networks, people deal with sort of serial update, where you update one global state at a time. Do people do that with these cellular automatons? And I imagine the dynamic would be different.
Oh, sure. Yes. Yeah. This is just a hint at how we can extend the dynamical systems ideas. There could be other update rules. So what I'm going to talk about today is the simplest one, this implied simultaneous update of all the sites at once. For example, you could have what's called asynchronous update. Imagine you had a little radioactive atom at each site, and when it did this little decay thing, you updated. And then so the sites are kind of firing off and on all over the lattice, and that actually, even for the same local function phi, leads to very different behaviors. Yeah, so you can do it serially. Again, that will change the, yeah, right, so what we're talking about here is that part of the architecture that is the update rule for the lattice. And as you vary that, you can get different behaviors too. So today I'll just show you two classes where it's simultaneous update. Okay, so we have kind of arguing that even though this is a spatially extended system in infinite dimensional, it's still a dynamical system with a state space and with a dynamic. We have the equations of motion written down, and at least formally, we start from some initial condition and it traces out a trajectory in the space, now infinite dimensional. A lot of the ideas we developed before were looking at invariant sets and stable manifolds. So the question is, how do those tools, are they even useful for this infinite dimensional setting? And the answer is kind of mixed, yes and no, or no, but you have to maybe yes if you work harder. But there's some sort of overall comments one can make. So generally, what does dynamical systems theory have to say? This is kind of state space view. Everything we've worked on so far and introduced have been about low-dimensional systems, one-dimensional maps, two-dimensional maps, three-dimensional flows, that sort of thing. And a lot of the argumentation was based on visually being able to see the structures, like hyperbolic, stable, unstable manifolds around a fixed point, that kind of thing. Infinite dimensions, well, it's not immediately obvious. Again, in a sense, it's kind of a criticism of this view that we just have a state space where the states are just points. There's no internal structure. Whereas now, well, the states are points in this infinite dimensional space, but actually, if we look inside, that's actually this infinite vector of numbers over the lattice, and there is this notion of contiguity and closeness. So dynamical systems theory proper doesn't immediately address that, kind of throws that information away, and perhaps to some deficit. What are the invariant sets for these infinite dimensional systems? Are there attractors, fixed points, limit cycles? What's going on? Right? You'd like to at least see some of these simpler invariant sets there. What does stability mean in an infinite dimensional space? Remember before we had the notion of attractor, we had this invariant set. It goes back to itself on the dynamic. Stability meant to take a set larger than that, and that over time it got sucked back onto it. So there'll be some questions about how we can define that. Now, you can imagine one idea that extends fairly straightforwardly is if I give you the equations of motion for a spatially extended dynamical system and I ask, where are the fixed points? You know how to do that, right? I look for all those states such that the left hand, the change, is 0 for the differential equation, right? Wherever the x dot is. But that's an infinite set of coupled equations that I'm maybe linearizing around if I want to do the Jacobian. So, but there's some cases where you can actually work those things out. So, other ideas. How do we measure instability? Just the spatial systems, even though the infinite dimensional, do they actually track down to something, so there's enough stability. Also bifurcations, if we vary some parameter. What's the spatial analog of pitchfork bifurcation? What happens there? So I'll give you some kind of demonstration examples, some of how these ideas map over, or from dynamical systems to spatial extended systems. So not only are there the existing concepts from dynamical systems, but there are new questions. What's the role of neighborness, the role of spatial structure in the behavior of these systems? How do we deal with these two independent coordinates, space and time? And there must be some kind of interaction between things happening in time and how things propagate in space. So there are new questions that weren't part of the original low-dimensional dynamical systems theory. So, having sort of thrown those questions out in the air, I'll give some partial answers by way of examples, focusing on the cellular automata, discrete state, discrete space, discrete time systems, and then map lattices. One-dimensional maps on the discrete time, discrete space lattice. Okay, so first the cellular automata. Okay, our lattice is discrete space. Space is d-dimensional here. The examples I'll show you, mostly for reasons of visualizing them, just be one spatial dimension. So I can show you space versus time. Again, each site is indexed by I. We have local state space. I'll call that S here. That's the symbol. There's an alphabet. Now it's discrete. And there'll be, think of those, the alphabet just being the k integers. Again, we're just going to do binary today. We can certainly play around with non-elementary cellular time if you want. The instantaneous state or global configuration of a cellular automaton is just this list of bits at every site in the lattice. Neighborhood, the same idea. Around every site I in the lattice, there's some R neighbors on either side or in all directions that get included in the update function. It's going to be discrete time, so we take this neighborhood at time t, the state of the neighbors around I, and then the state of site I at the next time is just this function phi of that. So phi here is just it's just a mapping from bit strings, possible neighborhood configurations. Right? If I'm looking at nearest neighbors, there's my value 0, 1, and my two neighbors 0, 1. It means there are 8 possible neighbors. And then I specify phi as a rule or lookup table that maps length 3 bit strings to the next value, which is also binary. So and again, we'll just talk about synchronous updating. Phi gets applied in the lattice simultaneously across the whole
Can I ask another question?
Certainly.
Is the difference between the discrete and the continuous case, is this local dynamical? Basically, that it will be a continuous function for the continuous maps?
That's one difference, yeah. Depends on what you make continuous, right? I mean, I can let's see, right? So we could imagine. Let's see. So in the map lattices, I'm going to make the local state a real number on the interval. But I could imagine I stayed with discrete local state, discrete space, but continuous time. Slightly odd system. Maybe that's a little more like the asynchronous model. So you can imagine that there's a little stochastic automaton at every site, and it updates itself based on some distribution over continuous time. Like there was a little atomic, beta decay, and then as soon as the beta decay goes out, then I update. I look at my neighbors and update myself. So that would be one type of. At this point, all things are possible, right? I had that table, I listed 3 characteristics: local state, space, and time. And each one of those can be binary. I only showed you 4 possibilities. There are 8 possibilities. Probably all, somewhere each one of those has some scientific use. But first things first, yeah. The simplest things first, yeah.
So there's some connection, there's some communication between the nodes in the lattice,
right?
Which is reflected in the little phi, right?
Yes, exactly.
So how do you know what the extent of the coupling is? Where does that kind of get?
That's part of the definition of the system.
So the eta?
Right. So eta depends on R here. Right. So maybe another way to think about this, in specifying a spatially extended system, there's a notion of neighborhood template. And that could, we'll do the simplest case, like just nearest neighbors or next to the nearest neighbors in a one-dimensional lattice, but goodness, you could be in a 2-dimensional spatial lattice and have some funny neighborhood shape to it if you wanted. And that's actually relevant sometimes for some systems, not being a homogeneous sort of circular or constant radius R neighborhood. Could actually have a shape even.
But S can have an arbitrary number of dimensions, and you may not necessarily be pulling in all of those.
Yeah.
Right. So when you say SI,
well, I mean, it's discrete. So what do we mean by dimension here? In some sense, I could say, oh, I've got 3 dimensions. In one dimension, it's binary 0, 1. The other dimension, it's A's and B's. The other dimension, it's alphas and betas. And that might, in some particular application setting, you might want to think of that. You might have current and voltage as complementary things, and now you've discretized. Here, just the simplest case first, to get some sense of what's possible, it's just going to be binary, or some integer. Part of the way I'm presenting it, though, this is something, just kind of invent these things and play around with them. And we have enough tools to actually make some progress in this. So I will just introduce two of the simpler kinds, but there's a lot to play with here. Okay, so, right, specify a radius, a neighborhood, dictating synchronous updates, and all those things specified, then I end up with this global map that's induced by those definitions. It takes the infinite configuration to a new infinite configuration. Okay, a few things here that will affect how we interpret these patterns. We'll get to some examples shortly. A lot of definitions here. So first of all, this local dynamic, this mapping, really just this lookup table from these binary, it's a local alphabet, binary neighborhood configurations to next state value. It's a function. I haven't added any noise or probability in there. It's deterministic. And that means that this global mapping, big phi, is itself a function. And as a result, this global map can be many to one. In fact, it's sort of rare to think of, when you specify your local dynamic, how to make phi be 1 to 1. So what does many to one mean? There'll be two different configurations at time t that map to the same next configuration. Imagine phi mapped everything to 0. Right? It's like all ones or peppering of ones and zeros, and all zeros, that's all going to map to all zeros. It's trivial. That's an example of an infinite to one global dynamic. Okay. The other consequence of the local dynamic being a function is that there is, in the sense we've been using the term, dissipation. There is shrinking of the hypervolume of sets. You don't get to create anything new. At best, you can just maintain local state information. So sets cannot grow. They can only shrink. Or in a few very rare cases, you can define, say, local phis that are maintain the number of ones locally, and then those are invertible, and then those will be volume preserving, kind of analog to Hamiltonian systems. But general case, and I'll show you a bunch of these, specifying a phi that is a function, it just induces shrinking. So it might, maybe that's a simple observation, but again, we need all the help we can get because we're now trying to understand something in infinite dimensions. So any basic properties are really critical. So even if it's in dimensions, I just argued here, these infinite volumes are going to be shrinking. So let's see what that means. So there can be stability. There's some hope that there'll be an analog and notion of a attractor in these spaces. Another interesting thing, and this is just pretty much a characteristic of the cellular automata, discrete state, local state. They're called Garden of Eden states, and these are initial configurations that you can never evolve to. The way we say that is that there's no, if the Garden of Eden state S, I look at what states could map to it. I look at the inverse of this, again, formally, and there'll be no such configuration. There's no way to make two configurations. So maybe that's a little puzzling. I already gave an example. Like the all zero rule. It maps everything to zeros. So certainly the zero configuration has a lot of predecessors, but the all ones configuration, that system will never evolve to it. You can prepare it as an initial condition, but in one step it goes to all zeros.
This is with a given dynamic.
What the dynamic is, take your neighborhood and map the next site value always, independent of what it is, to 0.
But a different dynamic couldn't do that.
Oh, yes, right. Change the rule, absolutely, yes. Yeah.
So within a given
Right.
dynamic.
The identity. So you ignore your neighbors and you copy your state value to the next time. All one configuration goes to all one configurations. So every configuration there is its own predecessor. So all fixed points.
I'm not sure what you mean by like sets. Sets cannot grow up. Sets of
again, so think maybe a little bit formally. I argued there's a state space. Now it's this by infinite space. Think of what a volume is there. What I mean is once you fix a volume, think of all of the, in this case, all the binary configurations that have zeros at even sites and a wild card at odd sites. That's an infinite set, and that's a set. And what I mean is that set, whatever it is going to shrink. Now there's a bit of an issue about how do I measure infinite volume shrinking. Okay, but at least we can kind of imagine how that happens, and there's a way to do that.
But you need, so I guess I'm also a little confused. So by the set, though, you particularly mean like the set of available states that could be evolved to? Or that
any subset in the state space.
Oh, the set of all the different types of, okay, now I see what you're saying. All the different possible messes, little messes.
Right, so what I'm asking you to do here is kind of forget a little bit. It's like half remembering the visualization ideas we had before. Volume shrinking, right? There's a circle around the Lorenz attractor that in forward time gets exponentially sucked down onto it. Think about that picture, but it's also in kind of more formal and in different dimensions. So, and there'll be a few gotchas in this. The low dimension intuitions don't apply sometimes, but that's roughly what the idea is. So. Okay. The other thing we can do, because it's discrete local state, discrete lattice, and discrete time, is we can ask how many different rules are there. So we can calculate the number of neighborhoods. So we have this alphabet of size k, to binary. And then we have the number of sites in the neighborhood. So if it was just nearest neighbor, we have radius 1 and 1 spatial dimension. Then that would be, well, I'm not specifying here what the template is. If it was nearest neighbors in 1 dimension, then it would be, in a binary alphabet, we would have 2 local states and 3 neighbors. Therefore, the number of neighborhood configurations would be the 8 3-bit binary configurations. So this would be 8. So roughly the number of neighborhoods, nothing else more specific said, goes as k to the r to the d. Grows very fast. The number of several time local rules, which are again these mappings from neighborhood to next state value, that goes as k to the r to the d. Grows very fast. And as you'll see, we're going to work with what are called the elementary CAs that make this k equal to r equal, well, nearest neighbors 1 and d equal 1. I point this out just because very often as you go to larger alphabet, larger k, and larger radius, the number grows just incredibly fast, and it's almost becomes cellular automata models become less helpful when you have many, many, many local states and coupled to lots of neighbors. And sometimes it's better off just approximating them with a continuum model. Okay, so how are we going to think about this? Get more specific here. Set spatial dimension to 1. So now we have 1-dimensional lattice, binary values at each state, and this goes off to infinity. Just to make this sort of graphically clear, the update dynamic is this lookup table I've been talking about, this rule that maps the 3 values in the neighborhood here to the next site value. So here, 0, 0, 1, you go down to phi, this little rule table. That's the neighborhood, and it says, oh, the center site should go to 1, and you place a 1. And then that's done simultaneously across the whole lattice. Yeah?
So the only difference between this and a Turing machine is just the fact that you have a sense of neighborhood.
Yeah. There's we can come back to this in the spring when we're more directly talking about the relationship between how Dynamical systems produce information and how that information processing looks like a kind of computation. But just to mention one little connection there, you can make a phi, although you have to, well, easiest construction is increase the alphabet size to about, well, one construction I know is an alphabet of 6 letters. Then there's a phi such that on some set of initial conditions, you can actually implement a universal Turing machine with a cellular automaton. So in some sense, what's going on, if you're not familiar with Turing machines, we'll introduce them later on. This is the tape, and I'm using some of the local state information to say where the read to write head is. And then the finite state machine control for the Turing machine is somehow mapped into this lookup table. And I share kind of dynamic state information between the lookup table and storing some of that locally. And you can actually get the, so what you would see here is this Turing machine that's operating, there's sort of an active site kind of moves around. Most of the lattice is quiescent, and there's this one little thing moving around, which actually leads to an interesting connection, first of all, with regular computation theory. But in this setting, you'd say, well, gosh, I have all these other sites that are just sitting out there. They're not doing anything. What a waste. You know, most of these pattern-forming systems like the CA examples, all the lattice sites are doing something. So the way we talk about embedding the universal Turing machine, it has a zero density of computation. There's only one site, one lonely site in the infinite lattice is actually doing some information processing as this control little finite head is moving around. Why would you want to build them? If I had a parallel system like this with all this infinite number of degrees of freedom, wouldn't it be nice to have them all helping in my computation? So that's the issue of parallel computation, which is still, of course, this big open question. So there's some interesting questions that come up. We try to map in. Later on, we'll map in some of the ideas from computation theory. First, we just had to figure out what can happen, right? So we're still just dynamical phenomenology.
Hey, Jim.
Yeah.
On that last slide, what is the LUT output bit string? What is that LUT?
Sorry, lookup table, that's phi.
Okay.
Yeah, there's a kind of historical terminology. This phi, sometimes we call it the CA rule. Well, it's just, I'll show you in just a second what that means. It's just a lookup table. I just specify all the neighborhood configurations and then what the center cell should go to. So neighborhood to next site value explicitly. So that's just a lookup table.
Okay.
Yeah. And some people built discrete circuit simulators to do these things and literally used chips, lookup table chips. So now the elementary CAs here are one-dimensional. We're going to have a finite number of cells and wrap them around periodic boundary conditions. We have binary local states, just nearest neighbor coupling. So that means the neighborhood, each site looks at its neighbor I minus 1, neighbor I plus 1. That's the 3-bit that gets plugged into phi, the lookup table, and then we get the next site value. The number of these, now we can be more explicit. The number of possible CAs is k to the k to the 2r plus 1 if we have a symmetric radius r neighborhood. In the case of the elementary CAs, like I said before, we have 8 neighborhoods. There are 3 bits in the neighborhood, so there are 8 possible configurations. And then the number of possible phis, rules, is 256. That's 2 to the 3. Right, I have I have 8 neighborhoods, and I have a choice for each one of 8 neighborhoods, whether it's a 0 or 1 for the next site value. And the total number, that's 256. Now, you can simplify things a little bit. It's not too hard a calculation. If I don't care whether I represent the on state or off state of each site, the local state, as red or green, black or white, 0 or 1, then there's kind of a equivalence. I consider these the same. Also, if it doesn't matter if I'm giving how I index from left to right, being site 0 up to site n, or vice versa. So under those two exchanges, there are really only 88 different equivalence classes, distinct behaviors. So I go down from 256 to 88. And these are finite enough numbers. People, for years, did exhaustive studies of all possible elementary cellular automata. So one quick thing that's kind of handy, this is a notation introduced by Stephen Wolfram. We can look at, for a given cellular automaton local rule, this mapping from neighborhood to next site value. Well, we have a canonical lexicographic ordering we choose for the neighborhood configurations. And then we read off the output bits in just that same order and then turn that into an integer. So this is, this is the least significant bit, most significant bit. So the 1's bit, the 2's bit, 4's bit, 8's 16 bit. So 2 plus 16 is 18. So we call that lookup table elementary cellular automaton 18. So I slip into this all the time. Those of us who study these things, they say, oh, Rule 54 and Rule 110 and so on. That's what we're referring to. It's this specification of the output bits on the lookup table. that we converted to integer, just a nice shorthand. And like I hinted at before, as soon as we get to alphabets of size 4, 5, and 6, and next to nearest neighbors, this numbering scheme is kind of useless. But at least for the elementary CAs. If you ever go to a Cellular Automata conference, you'll hear everyone, because they have their favorite, they're studying elementary CA 22. They'll have a whole session on what is Rule 22 doing. Okay, so how are we going to look at this? So one of the key ways of visualizing how the cellular automata behave is in terms of a space-time diagram. So I start off at time 0, I specify some initial configuration here, just some arbitrary bit string, 0s and 1s, and then I just plot the successive configurations over time. This happens to be Rule 18, but I'll talk about that a little bit more. And then the other thing I'll do is show you the space-time diagrams where the underlying lattice is not infinite, but in fact periodic. So here, this is a 50-site lattice. Site 49 is the neighbor of site 0. So in fact, mathematically, you should think of this as a cylinder. Okay, now kind of a tour of what can happen, right? So we have this space, potentially 256 different dynamics, different rules. I just argued there are really just 88 ones that could be different. We just do a survey of what are the interesting behaviors over this class of elementary CAs. So I'll do this in kind of in mirroring the order that we introduced dynamical systems. So Rule 8. So again, I said Rule 8. That's this binary thing. So you should think of the 8 output bits. That means the third bit's turned on in binary, just one on bit. Well, basically, whatever initial configuration I start with, this thing, in a few steps, goes to all 0s. So you can play with this with the Cellular Automata lab I put on, right? The Rule 8. Try different initial configurations. There's a way they're having it generate random initial conditions of your lattice. And what you'll see is for Rule 8, pretty much everything goes to 0s. So you think, well, first of all, what's our dynamical system interpretation? 0 seems to be a fixed point. Obviously, down here at time 13, 0 goes to 0. Just almost, it's a visual proof that 0 is an invariant set that's a fixed point. And if you try probing it with different initial conditions and you see that they all come back, that means there's some neighborhood around 0 star, all 0 configuration where I'm flipping bits, that gets sucked back onto it. Okay, so there's some hint that although this could be an infinite dimensional system, that 0 star is an invariant set, it's a fixed point, and it's a attracting fixed point. And now the fun starts. So here are 3 different example CAs. This is Rule 204, Rule 140, and Rule 79. I think they're all starting on the same initial configuration, just to compare things. What happens here? Well, basically every bit. If it starts off at 1, if it stays at 1, starts off at 0. In fact, if you go look up Rule 204 and you lay out the lookup table, what you see is that it's just copying the center bit in the 3-bit configuration, which is just, so it's just the identity map. Kind of trivial. Fixed point. Like every configuration is a fixed point. And none of them are stable. Now, Rule 140 here, what you see is how to describe this. And we'll talk a little bit later on about how to describe these space-time patterns. But one of the things you notice is that if there's a 1 anywhere, it's bounded by 0s. So the texture is here basically columns of 1s that are separated by some number of 0s. In other words, I don't find 2 1s together in a column. So there's some kind of inhibition there. So there is actually kind of a regularity that we can describe in this. And once you describe this regularity, it's basically that I can have columns of 1s next to 0s. Talk about how to use automata theory to represent binary string sets like that, you can show that that set is actually invariant. And it's also stable. And you can see the stability up here just a little bit. Again, you can play with this with the Sage lab. You can sort of see, starting with different initial configuration, you see the same thing. You see wherever there's a 1, it contracts down to a single 1 then. So there's kind of a stability. I can take this configuration and flip some 1s around here, and those are all going to be shrunk back down to these columns of 1s. So there is a vicinity around this collection, infinite collection, of so randomly placed vertical width 1 black columns that this vicinity will come back onto it. So there's a sense that, again, fixed point, kind of trivial. Everything's fixed point. Here, okay, this actually has some basin of attraction around it. And it's fixed point and stable. So. Rule 79 is actually another kind of example of this, except maybe one is a little harder pressed to sort of see what the regularity is here. Here I can have columns of 1s of width 1 or width 2. And then those are separated by isolated zeros. That's it. So there's actually a way that we'll actually learn the sort of automata theoretic description of the spatial structure of these patterns. And you can show that this not only is an invariant set for that elementary CA, it's also stable in some sense. So again, I'm kind of anticipating a little bit some other tools we're going to bring in. But here, at least the first cut is we do have fixed points. This is what they look like. The same pattern comes back to itself after time. By experimenting with these particular cases, you can convince yourself that there is a type of attractor you're going to that has sort of regularity in the spatial structure and that it's stable. Okay. Dynamically, these are kind of trivial, right? As soon as this relaxation period ends, it just copies whatever's going on. So it's kind of, once I get down to a fixed spatial pattern, it's essentially the identity now. Not very interesting, especially for a spatial system, but there are other examples where we have things moving around in space and time. Okay, so here's Rule 99, Rule 51, and Rule 35. Now what do we see here? Again, you can go play with this rule. So starting from different initial configurations, at least at long times, we get this homogeneous checkerboard. So the configurations are not fixed points, right? They're now limit cycles, period 2 limit cycles. So here, say even time, I have 1, 0, 1, 0. The next time it would be 0, 1, 0, 1. So I get this checkerboard in time. Pretty regular spatial structure. That's easy to describe. Regular temporal behavior. Same thing down here, Rule 51. Maybe a little more complicated. Why? Well, because I'm seeing these bands of different sizes here, kind of like the randomness we saw before. But within the bands, things are obviously period 2. So here, I have all zeros, some small configuration, all zeros going to all 1s, going to all zeros. So that's periodic. There's another little region over here that, kind of like this, like a little piece of this. It's alternating zeros and 1s spatially, and then that flips. So it's also period 2 here, but has a different spatial structure. And you can sort of see that pretty much just, as soon as it settles in, it's quite predictable. So not only do we have local periodicity, like a local limit cycle, the entire global configuration repeats after that. So limit cycles, periodic sequences of spatial configurations. And then here's Rule 35, which is, now you see it's actually just propagating off to the right here. And again, there are these regions of kind of synchronized oscillation and then exactly out of phase, the spatial shift. There's a relaxation period here, things mapping down. Again, maybe it's a little bit more obvious here. Rule 99 start with arbitrary configurations. We see these sort of little white, I mean, call them particles if you will. We will do that later on. So as a white particle hits a black particle, they annihilate. And then what's left over is this homogeneous textured region. So there's some initial period of time in this artificial universe. You know, it has its own first 3 minutes. We put in these random initial hot configurations, and it's cooling off and simplifying things. And that's also kind of a hint that this limit cycle here actually can be stable. Many, many initial conditions are mapping down to this one kind of, well, this one series of states. So there might be a vicinity around this that's getting sucked down onto it. So again, that's why I was belaboring the point about there's dissipation. Because there's a local function, the net effect is contraction. I could put in any initial random string, and then this just goes to the checkerboard. So there's some shrinking in the state space and simplifying the spatial pattern.
So rule 99, I can see that that's a limit cycle because, and it's stable because you perturb it, it's going to go back to what it was.
Right.
Rule 51, though, I'm not sure I can intuitively see that that is stable because if you perturb that, it seems like you're going to get a different pattern going forward.
Right. So A, go do that with the lab. And actually, Rule 51 is actually, it's the identity plus a bit flip. So actually what I said before about the identity applies here, except it's just alternating. So in fact, every configuration is period 2. And just because I'm flipping the bits, it's going to cause it to oscillate in time. The initial, wherever the zeros and ones are here, those are fixed.
But doesn't it have to come back to the same state after it's perturbed in order to be stable? I mean, if you do that.
Right. But no, what you said was correct. If I flip a bit up here, then I'm going to say widen this black region. So in other words, I would perturb the smallest distance. Well, because we're in a discrete space, I don't have epsilon anymore. Epsilon is 1. Right? What's the smallest change I can make? Flipping a bit. And that can actually, as you'll see, some big changes in how things evolve. There's not, so we don't, so the problem or issue with, you guys still there? Sorry. It says it online, so yeah, we should wait for it. It is. Well, I do happen to know that UCs are, we have nice fiber between campuses, so there's no reason I should be using this.
But you could have connected cage together so that you would be opposite side of the country and show virtual environments. That's wonderful.
Actually, we were just talking about stability. How robust configuration was perturbations.
Ask a professional here.
Sure, if I can manage.
So, I'm curious, in terms of physical information, let's say you're specific, could you look at Rule 51
You might be a little hard pressed because the geometry is so discretized to carry over. People, there are we study some one-dimensional, two-dimensional sort of I'll show you some kind of analog here. These are just the simple ones. Hey there. Sorry. Are you there? Oh. I can hear you kind of. Wow. Hello. Hello.
But how much of a help do you really use it? It's UC.
Well, right, but this is going to have to Skype servers. I'm not looking at that. Then we can use like some systems. This is going back to Hey.
Hey.
Yeah. Okay. Well, actually, Skype's been pretty reliable so far, so I'm not going to fault it too much. Okay, back to where we were. Okay, so let's see, what were we talking about? Oh, some examples here. Yeah, but let me push ahead. There's more to, and I'm kind of stepping up. I'm picking out in the space of 256 rules some interesting things that can be laid out in the classification scheme we developed before. So now here is rule 109. At some point, these rules, just play around with them. This is a kind of some sort of mixture of local fixed points down here, these little columns of zeros, and then they kind of form local boundary conditions to different kinds of periodic patterns. So here, okay, it's a kind of checkerboard with the whites always bounded by zero. The whites always bounded by black, sorry. Kind of a regular pattern here. See, there's this little kind of house-like thing going on here. Maybe it gets a little wider if I move the columns apart, but then I can have them a little bit out of phase. And then this one's some bizarre mixture of like this upside down U's, small U's, and individual dots. So now this will repeat. I mean, I can take some segment of this, and that takes a little longer to figure out what the period is. Right? What do I mean by period? You pick some configuration here, and then you look forward in time until it repeats. As soon as it repeats, of course, then it'll exactly repeat again. But now this is a complicated spatial pattern, so visually doing the matching is harder. You could write a program to do the matching, of course, that would tell you what the minimal period is. So not as simple as the other limit cycles. There's some kind of diversity, and a little bit you can almost analyze this in terms of, well, if I have a region here that's bounded by these white columns, kind of like fixed boundary conditions, not in some sense, no information flowing across or perturbations aren't flowing across that, I could just sort of count up the cycle length here and the cycle length here, and then the overall period would be some product of those cycles. So there'd be a little more analysis you could do for this. And this is also kind of typical. What's going on here? It's a spatially extended system. So when I start with some random initial configuration, the sort of one region, the sites start to talk to each other. Maybe they kind of synchronize, or even kind of generally synchronize. And over here, they start to synchronize. But as time goes on, they don't agree about what synchronization is. And then we get some region of disagreement. So locally, what's going on, there's a type of local in space contraction or synchronization, simplification. But globally, those regions can get attracted to simple fixed points, limit cycles, independent of others. But then the whole lattice, spatial structure, is some sort of product or composition of those things. So there's a kind of modularity here, which is part of the system being spatial. Because each site is only talking to its neighbors, if I perturb a site, that information can propagate at most one site per time step. So we say the speed of light is 1. It's determined by the radius. When you have a finite speed of light, perturbations can propagate only at finite speed. That means distant regions that haven't communicated yet can sort of be doing independent behaviors until finally there's enough time for them to communicate, and then they just disagree. Something could be a fixed point here and a period 2 limit cycle here, and there'll be a boundary disagreement. So it becomes a little more challenging in these cases to imagine what's going on, but you can say some things. Okay, so you might think of this a little bit crudely like the analog of quasi-periodic behavior. Remember, quasi-periodic behavior, we had these torus attractors and these relatively irrationally related frequencies, different kinds of oscillations. And because they weren't exactly phase locking, it kind of filled out this larger set. And a little bit, that's kind of an analogy here. So we had limit cycles. These are maybe some kind of very discretized analog of quasi-periodic behavior. And of course, chaos. Well, that's kind of an issue. What do we even mean by chaos here? Remember our basic properties. So maybe the first cut is it just looks complicated. Complicated orbits. So this is rule 90, rule 18, which I showed you the lookup table, and rule 22. And these are some of our favorite complicated CAs to look at. Turns out, and this is partly a product of my having stared at these space-time diagrams for far too long, despite the sort of complication you see, this kind of texture, motley texture, there's actually quite a bit of structure in both of these diagrams. But we're going to have to wait until basically spring to figure out how to describe what that is. I mean, there are some patterns that you see, though. So let's look at rule 18. There are these big white triangles here. So what's going on there? You can do a local analysis. If you have the lookup table, rule 18, if you remember, it's simple. All the neighborhoods, the 3-bit neighborhoods, they all map to 0, except for 2 entries. There was 0, 0, 1, that maps to 1, and 1, 0, 0 maps to 1. So what happens is there are a bunch of local neighborhoods that all map to zeros here simultaneously. That determines how wide this triangle is. And then if we look at the 1 bit sort of coming into the white region, into the 0 star region, that's the activation of the rule 0, 0, 1 maps to 1. Right? 0, 0, 1, and then I map the center cell to a 1 now, and that propagates a bit in. And then the same thing for the other sort of lookup table entry, 1, 0, 0, that propagates a bit in this way. So rule 18 is actually pretty easy to describe at first glance, the white triangles. It's like there's a saturation dynamic, everything resets to 0, and you can convince yourself that 0 star, zeros, is a fixed point. So any region of zeros maps to 0. And then one bit's propagated. So that explains all of that. You can kind of write this out. Tell people to calculate some of the statistics if you detected that. There's a lot more structure going on in this. So even this, there's kind of a white triangle thing, this kind of reset, information propagating. Same thing here, roughly the same argument works. Turns out the white triangles are the least interesting things in these space-time diagrams. So they're actually little particle things moving through all of this of different structures. So we won't be able to do a complete analysis of Rule 18 until we have some more tools from how they're actually quite structured. Certainly, texture. The density of zeros and ones is slightly different. It's fine, but they're very structured. Okay, so this visually it's just complicated. That's the closest parallel with what we meant before when we gave a definition of a chaotic attractor, right? Attracting invariant set that has positive, at least one positively Lyapunov exponent or this entropy rate quantity was positive. So what would be the analog of a Lyapunov exponent? So what you can do, so here are the same three cellular automata. Remember how we did the dot spreading, or the way we thought about Lyapunov exponent? I had a reference trajectory, and then I just perturbed, made a little epsilon perturbation, and then I tracked two trajectories and looked at how that initial small separation grew exponentially, and that exponential rate of growth was the Lyapunov exponent. Okay, so why not do that construction here? Okay, it's a little tricky, right? Because now we're in infinite dimensions, but that shouldn't stop us. I have a point. Okay, let's say the all-zero configuration. And then what I'm going to do is just flip one bit. And that's the smallest difference I can make. And then I'm going to plot the trajectory, which is the difference vector. So I propagate 0 star forward. I propagate 0 star with the 1 bit forward. And I look at the difference. So that's what I'm plotting here. And what we see is that, in fact, even one small, for rule 90, one little bit flip actually causes this cascade of difference that propagate out in space. So in fact, there is separation between these two trajectories. Same thing for rule 18, same thing for rule 22. So we can look at the spreading rates. Probably better to call them spreading rates, not Lyapunov exponents, but the construction is motivated by the previous idea. So the number of different bits, so we can use the number of different bits between 0 star and the propagated one to be a measure of distance in this infinite dimensional space. Grows and grows and grows. Yeah, I got a question.
So, I mean, it sounds like it really depends on your base initial condition that you're comparing to.
Right. Right.
Is that a problem? You have to have a description for your spreading.
Well, but that was also true with the Lyapunov exponents, right? So it's one thing for me to try to measure the Lyapunov exponent for the Rissler attractor, and I have to start with points on the attractor and look at the little frame that gets carried along and how those basis vectors are stretched and shrunk to get the full spectrum. But I could have started, 2 miles away in another attractor there. Same thing here. It's true that there may be a dependence of the spreading rates on what the initial two configurations are, where they are in the state space. Yes. In fact, we already argued, like for the identity, that these spatial systems have an infinite number of fixed points. So there could be many, many, many basins of attraction here. In fact, infinite number is kind of a typical case. So again, we're a little bit kind of get our head around that, but it's not as visually apparent compared to the differential equation case we were looking at. Okay, so this is some first cut of what we might mean by a spatial extended system being chaotic. That small variations get amplified. In this case, propagated in space and time. You can try this experiment for the others. I probably should have the figures for this, but for the periodic limit cycles and the fixed points I talked about, you do that, and indeed, there's no spreading. So you can try that with the lab. Easy experiments to do. It's mostly just kind of playing around with different initial conditions. Now the other thing that happens with these elementary cellular automata and spatially extended systems generally is that they don't have this first 3 minutes kind of cooling down and simplifying to some kind of attracting invariant set. They can have very, very, very long transients. So this is rule 54 from time 0, starting from some arbitrary initial bit string, going 100 steps, and then jumping ahead, iterating a bunch, and then showing you what it looks like going from step 2574 to step 2673, much later. So initially, again, actually squinting your eyes, bad video actually helps with this. There's sort of more complicated early phase, so it is like it's cooling this first 3 minutes of simplifying things down here. You find these more homogeneous regions of texture, these big white triangles sort of disappear, and then at long times what you tend to see are these columns of large and also sometimes small white triangles. Things are simplified down. And then you can kind of tell I'm giving you a big enough swath of time here, and in fact this is a temporally periodic pattern. It's a limit cycle. So it's just kind of a feat. If I change the initial condition, one of the things that can happen is that these might occur over here, or I might have 3 of these here and 1 here, and so it would be very complicated basis of attraction for these limit cycles here. So these long transients are actually quite common. Probably the most famous elementary cellular automaton is this one. It's Rule 110. Like Rule 54, it has this very long period. In fact, this is quite extended, over 100 time steps. It's not even clear. It's really settling down to a complicated background texture here. But if I jump ahead about 600 steps, I end up seeing that there is some sort of background regularity. You kind of see this is actually kind of a tiling, periodic tiling of space and time texture map here. You have to kind of count a little bit. It's period 4 in time and period 7 in space. There's a little tile. And then we have this funny thing through here, obviously a different texture. So one of the ways that you can't help but look at these space-time diagrams from cellular automata, partly just the way we see things, we want to think about these background textures that are kind of like the vacuum states. These are sort of harbingers of periodic orbits. But then there are boundaries between these that we look like particles moving around. So the reason Rule 110 is famous is that someone showed that there are sets of initial conditions that you can choose such that you can encode any problem and do any computation. So in other words, you can embed, or I should say, the time evolution of Rule 110 over these special programmed initial conditions is equivalent to a universal Turing machine. Again, it's not very efficient because most of the lattice is quiescent, but the ways of using these particles to store and process information. So I'm jumping ahead a little bit to some of the ideas we'll develop in the spring, but these particles store information in their temporal phase, and then they can communicate that across space. You implement logic, in a sense, by colliding different kinds of particles together. You have an alpha particle and a beta particle. They store different kinds of information about some previous region, some previous time, previous region at previous time. They come together, they form essentially logic gates. So that's how this construction by Matt Cook turns Rule 110 into a universal Turing machine over a very particular set of initial conditions. But Rule 110 has rich enough pattern-forming properties, rich enough background textures, so-called domains, and particles that you can use a subset of those to implement a kind of spatial logic with the particles. We can also look at are they chaotic? Well, okay, what we have now so far is just a spreading rate measure. And so yes, in fact, Rule 54, although it mostly settled down to a regular background texture with a few of those fat vertical particles that are just sitting still, perturbations do propagate in space, just with one bit flip. Now Rule 110 is actually really peculiar. Perturbations, this one little bit flip, only propagates to the left. It's very strange. But it happened to be very useful in the construction, construction of Rule 110 being universal. Let me just finish up with just some demonstrations that maybe survey a little more broadly what can happen with the elementary CAs, just mostly kind of a show and tell day for these different kinds of spatial systems. Hopefully the argument is at least a little bit compelling that some of the ideas from general dynamical systems can be brought over. We won't be able to tie that story up until the spring. We need some more ideas from the theory of computation to do that. Okay. Okay, good. Here we are. Okay, so, right, so we just finished up. We did a survey, Monte Carlo survey of elementary cellular time with radius 1 and radius 2. Showed you what the periodic boundary conditions look like. Most interesting thing was to take this pure dynamical systems view. Basically, that you can show that this global mapping that we were talking about, that maps one configuration to the next, the global dynamic for the cellular time, can also has this other representation of the square onto itself, unit square. So now, one small modification. What we're going to do is have the local state space in our lattice system be continuous. Okay, so we call these map lattices. This will be discrete in time and discrete in space, but continuous local state. Now, if we have n lattice sites, the dimension of the system is going to be determined by the local dimension, say one dimension, and if I have n lattice sites, I'll have an n-dimensional system. Right? If I had a d-dimensional local state and then a lattice in 1 and 2 spatial dimensions, I have a very high dimensional mapping. But it's a discrete time mapping nonetheless. We have a neighborhood just like before. Notation gets a little bit messier here than with the cellular automata, but the idea is exactly the same. You could call these cellular map lattices because there's a notion of neighborhood that's here. And what happens is that there's a local dynamic before. I'll still denote this phi. But now we take the local configuration, the dimension which depends on the radius, the number of the coupling from one site to its neighbors, and takes that neighborhood to determine what the value of the center cell is at the next time. So it's a mapping from, let's say, if we had one dimension and it was an elementary cellular system, we had radius, that means we look at our two nearest neighbors and ourself, then phi here, it's a function, no noise. Then the neighborhoods are in a three-dimensional space, and we map down to a one-dimensional space, which is the state of the site at the next time. And we make the same distinction here. There's this local specification of the system, given by this local rule, lowercase phi, but then what's actually happening is we apply that simultaneously across the whole lattice, just like with a cellular automata. And then we have this global map that takes the global configuration of the whole lattice. That's the vector of all the states locally, and then maps to the next global configuration. So why do this? Well, there are some different things, one of which Chris just asked about. The cellular automata are all discrete on a finite lattice. And there's sort of in the show, you're just looking at some long periodic orbit. Here we have continuous local state. So we have notions of closeness. Basically, geometry is back. We have a notion of closeness between local state values. Before, in the cellular automaton, the closest that two spatial configurations could be was one site, one bit difference. Here, the distances can be arbitrarily small, so we have a nice notion of closeness topology and geometry and so forth. The dynamical systems ideas that we introduced already most directly apply to continuous systems, so they apply here. We have all the qualitative dynamics. We can now talk about doing bifurcations. There's a notion of a parameter value that can slowly change to look at bifurcations, even though these are high-dimensional lattice maps. In cellular automata, there wasn't really a natural notion of even one rule being close to another, let alone one way of parameterizing between them. People have tried, but it's usually not very helpful. And if we want to get quantitative, these are continuous state dynamical systems. Therefore, everything I said before about instability, exponential separation and contraction, dissipation, all those ideas, and in particular the Lyapunov characteristic exponent spectrum applies. So these are great tools. It wasn't immediately clear how to measure instability when we talked about cellular automata. I sort of hedged a little bit about what a chaotic CA was. I mean, visually, Rule 18, Rule 90, they look kind of noisy and complicated. The way I talked about it was to look at what are called the difference patterns, if you remember. You take one pattern and a pattern next to it that's just different by 1 bit, and then you plot in the space-time diagram how the differences grow or not. And if they grew, then we call it tentatively chaotic. Here, we have continuous states. We can actually have exponential separation in a well-defined sense that we talked about already. So old tools we can use to be more precise about what's going on in map lattices. And there's actually some new ideas. So I'll illustrate these. Before we had, remember with Lorenz and Rissler, we had maximum X or maximum Z return maps, a way of reducing the dimension from a continuous flow down to a discrete time one. And we're always looking for ways to reduce the dimension so we get some visual handle on what's going on. Well, here, we're in n-dimensional or essentially infinite dimensional systems. Any way we can reduce the dimension is helpful. So I'll show you a couple cases where we can use spatial return maps. I'll look at how one site predicts or doesn't predict the next site as I scan down a spatial configuration. And also now we can imagine that there are little perturbations, they move in space and time. So, and it turns out that the way we measure the spatial propagation of perturbations, like those difference patterns for CA, it'll be clear that spatial propagation of instability is not the same thing as the Lyapunov exponents. Okay, so let's a little preview. So, simple case, and we'll just work through this in a little bit of detail and try to illustrate some of the new phenomena that can occur and how we can apply regular dynamical systems tools to explain how a lattice of maps forms patterns. Okay, so this particular case is going to be the logistic map. Easy to make a cartoon of this. Every lattice site has a continuous one-dimensional state space, the unit interval, and then there's a map. Okay, all across the lattice here, discrete spatial lattice, and then there's some coupling between these that we get to specify. And I'll just choose simple additive coupling here, typically. So the local state is in unit interval, and then here's one example of how to couple logistic maps. So every site I, we have the familiar quadratic function r times x times 1 minus x. And what I'm going to do here is just look at the value of the site to the left and right, essentially take the average, and then there'll be a parameter, C here, that gives the coupling strength, how much the neighboring sites perturb the center site you're interested in. Now, why do this? Well, in isolation, we presumably know a lot about what the logistic map does, so it should be a little bit familiar. And in particular, we should know exactly what's going on when C goes to 0, right, when they're independent. Okay, so that's the idea. So
Can we ask you a question?
Yeah, absolutely.
On the previous slide, so when you build the global space, you don't take the metric of the lattice into account. I was wondering if it's possible to construct the metric of global space. Is it possible to take the lattice metric into account to incorporate it?
Okay, I'm missing the word. Did you say metric?
Yes, I'm saying metric. In other words, if 2 points are close and they differ by close in the lattice versus by far,
Right. Yeah, so in the case, and we were kind of talking about the metric to use for cellular automata, when I presented that XY plot on the unit square, and I made a choice. I took, there was a window of 20 sites. I took 10 on the left and put a binary point in front of that and called that the X value. That then makes it a number between 0 and 1, right? And then, so I'm metrizing it by, there's a, most significant, next most significant bit, and so on, and they're weighted by powers of 2. And same thing with the left half, and calling that the Y coordinate.
Right, but in a more general picture where you have the state of this real or some kind of k-dimensional state in every point of the lattice, now you want to compute it as a global system where you take R to the Z or something, as your state space.
Right.
And then you just take your metric, and when you're talking about dynamics, it's good, but you're using metric in this space.
Right, well here, just think of Euclidean metric, like for the logistic map lattice. Right, so at two different spatial configurations are a vector in The lattice has n sides, n dimensions, and we'll just use the Euclidean measure of distance.
That's right, that's right. So what I'm wondering is, if I wanted to do somehow the metric on the lattice into the picture, are there techniques to doing this?
Oh, you mean for the map lattices, could I do this, what I call the dynamical systems plot? Is that the idea?
Well, so in the Euclidean metric, right, if two systems differ by the same amount in the adjacent
Right.
spots, it's going to be the same distance as if they differ across
Oh, right. No, I see what you're saying. Right. Well, okay. So that is kind of the idea. Right. So just to kind of bring this together. Right. So if I have my n logistic maps on a lattice, and they're two different configurations, I have these two vectors, and it's sort of very the distance between those is not weighted by how spatially close they are. So that, I mean, exercise, a good idea. I'm trying to think about how you would do that. It's essentially what I just said. If there's some way, and I'm not sure I'm going to propose a particular idea right now, but good to think about, what would be a good way to adapt that binary string metric to this case? Okay, one way we do that, but this is next week, is we can take the continuous system and actually replace the continuous state with discrete symbols. And then in that case, we would take the map lattice and turn it into it's called symbolic dynamics. We will get to this. Then I would have the sort of data from the map lattice, the spatial configurations would now be discretized, and I could directly use that previous metrizing to think about this mapping of the square onto itself.
Okay,
yeah. No, it's a good question. No, but other than that, I'm a little bit, it's a good idea. It's a good idea.
Well, I mean, I was thinking we take, instead of embedding at a single point as a value, take that as a dimension, we take the kind of neighborhood.
Yeah.
And use that as a...
Right. Yeah. Well, I'd be curious to see how helpful that was. Not hard to program up. I mean, all of these cellular automata and these map labs are very easy to program up, and maybe it's mostly just an exercise in some graphical programming to see if it's insightful. It's a good question. Okay, so, but how are we going to think about this, right? We have the logistic map. We know as a function of R, it goes through this period doubling sequence and chaotic bands, and period 3 and period 5 windows in the chaotic range and all that sort of thing. Question. As I start to couple these period doubling systems together, how do they interact? And what's the consequence for the kinds of spatial patterns they can form? Is this just going to be, imagine I'm kind of weak coupling. C is relatively small here. If it's small enough, you might imagine that as I sweep R, I'm going to get the full period doubling sequence, and the neighboring maps, say if they were uncorrelated, they just add a little bit of noise. So kind of a first guess, which is just relying on what we understand already. Imagine as a function of R, we have kind of a noisy period doubling bifurcation diagram. Okay. But first I want to suggest maybe something that's a little more fundamental change in perspective here. And it hints at the essential thing that adding spatial extent does to dynamical systems. So what we're going to do here is simplify things a lot just to get started, and so we can visualize what's going on. I want you to just think about two coupled maps. So much for my talk about infinite dimensions. This is just to get us thinking about what can happen in the full lattice. Okay, so we have two coupled logistic maps. So here we're going to have the same parameter value. So I have r times x, 1 minus x, and then the second map is r times y times 1 minus y. And then I just cross-couple these with the same coupling strength. I just add in the other map to a given one. Let me set the r value here to actually right at the onset of chaos. As if C was 0, the individual maps would be right at the end of period doubling just before chaos. So that's 3.56995, so on. But I'll add a little bit of coupling, 0.005, just a bit. That's pretty small. So again, if the coupling was turned off, we would know that we had this period 2 to the n orbit here. But now what happens is that we've added a small contribution from a neighbor. And what that does is, because it's small, it just takes the map and offsets it a little bit. So think about those green humps I drew before. A first approximation at the input from the neighbors just shifts it up a little bit. It's like a constant offset, which is intuitively going to maybe, you might think, push you a little further into the, past the period doubling into the chaotic regime. And that's roughly what happens when I add this coupling. So what I'm showing you here is the x map and y map coupled together. So again, the state space is now the unit square. And it turns out that what we end up with, if we just offset one map, we'd have these banded chaos attractors. But when we look at the system together, we have different attractors based on the relative phase of the two. I mean, if I just looked at one map, I kind of forget that, say, if it was a period 2 orbit, it was, even time steps, the value was high, odd time steps low for a period 2 orbit. But now when I have another system coupled in, what becomes important is the relative phase difference. If one is period 2 going high-low and the other is period 2 going high-low, then they'll, in a sense, be along the diagonal, but they could also be out of phase. So one is going high-low, the other one's going low-high. And that corresponds to attractors off the diagonal. So in this particular case, with this setting of the parameter values, in fact, what you find are let me get this right. 4 different attractors. I'll color differently, right? So we have pink, green, blue, and red. Those are all distinct attractors. And the way, why this many? Well, it has to do with the relative phase. So the individual logistic maps have been pushed by the input from their neighbor up to be more chaotic. So it's essentially like 4 bands. So if I were to project this down onto just the X map, I'd see there are 4 bands like that. But it's not in isolation. The actual state of the system depends on the phase and state of the other map too. So the pink 4-band attractor corresponds to the 2 maps tracking each other, although there's a little bit of chaos and they're sort of separating from each other and coming back, but they're constrained. So there's the in-phase attractor, and then there's the exactly out-of-phase, well, attractors, I should say. The blue one here, right? So one system is oscillating high, the other one is low, and then they kind of switch back and forth. And then those oscillations are modulated a little bit by the chaotic behavior. So even when we have 2 coupled maps, because the relative phase becomes important, and this particular system, the logistic map, is generating very high periodic orbits, there are all these different choices of initial relative phase that lead to different attractors, different basins of attraction. In this particular case, we have these 4 distinct attractors, depending upon how we set up the initial phase. You can play around with these parameters, so it's kind of a quick conclusion. If you play around with the parameters, lowering the R value or decreasing the coupling a little bit, what happens is that, you can jiggle the parameters so that you essentially can see the period 2 to the infinity orbits. And the consequence is you actually have an infinite number of attractors in the 2 coupled map case. Puzzled looks. So is the basic argument clear? Right? The idea is, again, just think about each map just being period 2. Okay, so each map is either high or low, and there'll be, and now imagine the global system is periodic, there'll be 2 distinct periodic orbits. One periodic orbit, period 2, where they're in phase, they both go high-low together. High-low together. And another where you chose the initial conditions, so they're exactly out of phase. they're not so strongly coupled that their behavior is knocking them out of being period 2. We're assuming they're still period 2. One is high, one is low, and then they oscillate like this, out of phase. So there'll be an out of phase, off diagonal attractor, or periodic orbit, period 2 orbit in that case. So I'm just drawing out the consequences of that observation. That now you imagine it's period 4. Well, okay, I've got A, B, and C amplitudes here, A, B, C amplitudes here. I've got 4 choices here, and there's 16 possible relative initial phases I could have for the period 4 orbit. So I'm going to have 16 possible different attractors, period 4 orbits, depending upon my choice of initial condition. And so you should think of these things as little basins of attraction here, and it just ramifies as I move the system further and further up to see period 32 in each period 128. Suddenly this state space becomes riddled with all these small basins of attraction that correspond to the different choice of initial phase for the orbits. And then the same argument works up here when we have chaotic bands. So here, in some sense, we have 4 chaotic bands, and we have a choice of initial phase. So in this case, we get 4 different attractors. Yeah.
Eventually, they'll become one band in that case.
Yes, as you increase R, right. So you can now try to imagine. It's harder because we have a 2-dimensional state space across R. Well, this is doable. We have fast graphics cards, so in principle, you could render this object in 3 dimensions and look around. And there should be some analog of band merging, where you would sort of suspect, given the closeness of the red and blue attractor, if I increase the coupling a little bit, it's conceivable. I'm forgetting whether at this parameter is true, but I increase C a little bit, that these would merge, and then I would just have one off diagonal and one on diagonal band attractor. Right? Yeah. So this is the basic idea to understand these spatially extended systems, these map lattices. The new thing is that relative phase, which we've been ignoring before. I never really even mentioned what initial condition we were using. In fact, that kind of doesn't matter where I start. I end up on the Cellular attractor. Here, when you're starting to compare two systems, the relative phase is important. And it's the relative phase in a spatial system that makes it do its unique things. Like relative phase difference can support propagating perturbations in space, for example, traveling waves and things like that. So phase becomes important here. Okay, let's shift back. Let's see if we can take that n equal 2 case and help us understand a little bit what's going on for a spatial lattice. Here, it's a logistic lattice over 256 sites, periodic boundary conditions, just like for the cellular automaton. And what I'm going to do here is, over space, to start with a sine wave initial condition. This will help, I think, emphasize the argument I was just making. R equal 3. So if you remember R equal 3 for the isolated logistic map, that's right where that non-trivial period 1 orbit goes into period 2. And then 0.05 coupling. Okay, so this times 0. Again, 256 values, setting the initial local state at each of the 256 sites. And then I iterate it 10 times. And I end up with this almost square wave-ish looking spatial pattern. So what's going on here? Well, you can imagine that, say, the lattice sites around here have relatively similar initial value, and that, and we're somewhere in this period 1, period 2 regime, if these are close enough, their differences will actually will decrease over time, and they'll start tracking each other in their period 2 oscillation. And that's what we see. There's a range up here where any initial differences after 10 steps basically go to 0. This range of sites, these are all exactly in phase and have pretty much the same value on the interval, same amplitude. Same thing over here, so apparently it didn't make that much difference that I started with large values here And then now I have these two regions that are in phase. If I were to show you time step 11, I don't have that. Time step 11, this would exactly flip over. Then there were another set of points, I should say sites here, that, again, their spatial differences decreased, and they made another region here of sites that were in phase, except the phase, the high-low phase, here differs from this. So you end up with this period 2 oscillation. So then, just keep iterating. Here's what we get for 20 iterations and 30 iterations, and what you see is that the region of in-phase sites gets larger and larger. They're sort of entraining their neighbors, and in a complementary way, the sites between these homogeneous regions get sharper and sharper. So just to introduce some terminology, I call the in-phase sites a domain. This would be another domain. This is a domain down here, and then between the two domains there's a wall. So the wall is where the sites are sort of disagreeing, or they're being pulled in two different directions. They have these neighbors that are doing this, they're out of phase, and they're being pulled this way and pulled that way. And then over time it just gets sharper and sharper. So you can actually calculate the values of these sites. I mean, there is a periodic orbit that this 256-dimensional system map is going to, and you can make various approximations to calculate what values these sites will go to here and here. So let's look at this in space-time. Okay, so this is just like the cellular automata, but now I have space. This is 128 sites versus time. You can see, so I'm starting with the sine wave again, so it's exactly the same system I just showed you, initial condition of parameter values. So immediately you can see there are regions here where the system is temporally periodic. Green, blue, green, blue, green, blue. And that, in particular, the sites that weren't in either domain get sharper and sharper and sharper up until about here. It's 127 steps. So I just showed you 30 iterations up to about here. End up with these domains. So this domain, call it even phase. This domain is odd phase. They disagree, and where they disagree, I'm calling this a wall. Then now the other interesting thing that happens is that later on, the wall actually becomes unstable. So we have these regions in-phase regions getting larger and larger. They're sort of pulling in the sites that are on the boundary between the two. It's sharper and sharper, but then that ends up pushing the system into, maybe you can see this, it's actually a checkerboard. So period 2 in time and period 2 in space. So in an interesting way, it's almost like the system is kind of having, over in time, going through a series of bifurcations. So the initial sine wave pattern, in-phase domains grow in size, recruiting their neighbors until the walls get so sharp that, in fact, what happens here is the walls are zero width. But then that means there's a cell that's looking to its neighbor that has a very, very different value, which is a strong perturbation to that edge cell. And that drives this instability, and then I get this checkerboard pattern, which eventually dominates the entire lattice. So we go through domain formation, walls, and then the walls are such a large difference, it drives the system into a different dynamic. Yeah?
This is very reminiscent of like an icing model about the randomness.
Yes.
So, I mean, can you define like a free energy or something like that?
Yes, you can do that. It's often, we'll talk a little bit about that with the symbolic dynamics. Yeah, how there's what's called a thermodynamic formalism as a way of thinking about energies here. Yeah. There was another companion lecture to this, which I'm going to drop, but maybe based on interest, that was going to go through Ising models and various kinds of stochastic spatially extended systems. So here, these are all just deterministic. Again. Okay. So now what I'm going to do is just to show you, this is again just kind of a look toward the phenomenology, trying to explain as much as we can based on our knowledge of the period doubling structure of an individual map. So I'm going to increase the parameter value R, so the map is taller now, to 3.4, then a series of diagrams here where the coupling strength increases. Okay, so here, more or less similar regime we had before. Coupling is 0.02, and I'm showing you, starting with the initial sine wave, like I had before. This is a very big lattice. This is 0 up to 2,048 sites. 1,000 steps in. This is the spatial configuration. So we talked about this. We had now these in-phase domains basically recruited all the sites. So every site in the lattice pretty much is either in one phase or the other and agreeing. But you can see here, it's sort of like a Gibbs phenomenon, Fourier analysis. You can see because these two sites are out of phase but close to each other, the difference between them is quite large. So the coupling is quite strong driving. So we get that, these little spikes there. In fact, if you went out to maybe 10,000 iterations, you'd see what I just showed you before. That these walls would break down into a checkerboard and have their own interesting space-time period 2 behavior. But here, what I want to do is take a snapshot after 1,000 time steps, iterating the initial sine wave, and then sweep coupling. And what we see here is actually a type of, as we increase the coupling strength, a kind of period doubling and then band merging. So here I'm going to go from 0.02 up to 0.05 in the coupling. And what you see now is instead of having period 2, there's actually 1, 2, 3, 4 phases. And consequently more domains here. And so one of the things you notice in one of the larger, in the lower coupling, was a single in-phase domain. It's now broken into several in-phase domains. Every site is going through period 4. But here what happens is you notice these have different sizes. That has to do with how that sine wave initial condition passed through the attracting part of the period 4 orbit. And sort of, how to say this, these sites here correspond to the bottom part of the sine wave, and they were close enough that they all went to the same phase of the period 2 orbit. Same thing over here. And then in between, we had points that were attracted to the other phase of the period 2 orbit. The same thing is going on here, except now, as I vary the amplitude in space, it's crossing over the regions in the local state space where I'm attracted to one or the other phase of the period 4 orbit. And then we get these different size domains due to that. Anyway, keep increasing. So now they're more strongly coupled. 0.06. What you see is we've lost the periodic behavior. Now it's noisy. In fact, it's 4 bands noisy. Overall periodic, but now with this chaotic modulation, until I go up to 0.075, I have basically 2 bands. Okay, so this is sort of a contrast or a similarity with before. I was arguing if we had weak coupling and thought about the behavior as a function of increasing R, so using the ideas of the picture we had for the period doubling, then I could explain the number of attractors in terms of relative phase. It's period doubling dominates. Then here, we're fixing R and sweeping C, basically just increasing the amount that the sites perturb each other. And in a sense, it's just shifting each local map further into the chaotic regime. And we see this period doubling as a function of coupling strength, not R, but coupling strength, and then band merging. And the parameter values where this happens, the actual values of the amplitudes can be calculated in terms of what we know about the period doubling behavior of an individual map. Now, what's interesting about the logistic map lattice is that there's something else that happens. There's something new that we can't, that's not, in a sense, anticipated, extending what we know about the period doubling behavior. So this is what happens, actually, if you go to very long times. Think back to that space-time diagram where the walls broke down to the spatial period 2, temporal period 2 checkerboard. That comes to dominate the entire lattice. So here I'm showing you, starting from a sine wave initial condition, iterating for a very long time, r equal 3, c equals 0.05, we end up with, so this is a 100-site lattice, spatial period 2, and temporal period 2 oscillates in. So this is actually the long-term behavior that the system tends to go to. And if I were to do a spatial return map, so I'm just, think of this as if it were a time series. I simply plot the next site value versus the previous site value. You can see there are these, well, actually 5 points here. Turns out that there's actually 2 domains here. So that's actually why there is this 5th point. This isn't shown here. It's from a much larger lattice. There's actually even sites are up, and then it reaches a place where the even sites are down. So there's a disagreement phase. We get this shift like that. Now, if I increase the coupling again to so they're more strongly coupled, 0.075, and I can go out for a long period of time, the system is mostly periodic, except we get this very interesting spatial modulation here. So here I'm showing you a larger lattice from 0 to 2048. And then what we do is the same type of spatial return map. So here we had spatial periodicity, and we saw points up here. Here, if we do this, what we see is actually a quasi-periodic attractor. So what happens is that in the logistic lattice, and this is not something that we anticipate, things that are period 2 and bands and so on, I can concoct an explanation and even think a way of calculating properties like I've been talking about. But this spatial modulation is actually quasi-periodic, and we end up with this essentially like a torus attractor here. So that's a time scale that I still don't know how to calculate. And if you watch this over space and time, what you see is that the phase. So I'm plotting basically relative phase here, and it's cycling around like this. That corresponds to waves, amplitude waves, propagating across the lattice in time. So we actually have traveling waves here. So before, everything I was saying was just trying to use the period doubling picture. It was sort of static in a sense, nothing moved. I was sort of arguing that the local basins of attraction were the dominant thing, period 2, period 4, 4 bands. I was using that and arguing, oh, they're perturbed a little bit, to argue for phase is important in many different attractors. Now here, this is completely new behavior, unanticipated. I'm not aware of any aspect of the period doubling nature of the logistic map that would lead you to think of these traveling waves in this quasi-periodic behavior. So new things can happen. Okay, so this was a bit of a shift. I only made one change to cellular automata. We just added these logistic maps to each site. Logistic maps, something we understand quite a bit about, and we can explain a fair amount of the behavior in terms of what we know in this sort of weak coupling limit. The local dynamic, the period doubling behavior dominates there. Phenomena of period doubling appear in space-time are interpretable. Something new, there can be an infinite number of attractors because relative phase is now important. And then we have these domains of in-phase sites and walls between them. So now with strong coupling, we get this new behavior, this quasi-periodicity in traveling waves. Okay, so let's do one more example of a map lattice. In a sense, this one is simpler, but perhaps we don't have the same intuitions about how to explain what's going on. But certainly haven't studied it so much. So this, I call this the dripping handrail. So the name comes from imagining that you're in, I guess, a couple months, you're in downtown San Francisco and the fog is in. And so there's a handrail and there's water accreting on this handrail, and you get this sort of extended meniscus under the handrail until some drop, until there's so much water that it drops off and becomes thin again. So it's very simple. Again, we have some local function of the state space. State space will just be the unit interval again, and we'll do a very simple coupling, but just like we did before, essentially the average of the two neighbors on either side. But then the local function I'm going to do is piecewise linear. I just have an offset. At each step I get a little offset, and then there's a constant slope. Then mod 1. So the way that looks like, so focus on an individual map here. So here's the, I'm drawing the sort of the temporal return map, if you will. I have the identity here, and then the green is what this function f is doing. So at each step, if I start with some initial water thickness, it gets thicker, 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 thicker until it reaches here and then it resets. That's when the drop falls off, and then it starts over again. So really simple. Some people use this model as a discrete time, discrete space analog of what's called an integrate and fire neuron. All that's happening locally is it counts up and resets. Counts up and resets. Pretty simple. Now what we're going to do is couple these together in the spatial lattice. Okay, I will explain what's going on, and then we'll do a demo here. So this is the space-time diagram. So here we start off with a random field, initial configuration, random values from about 0.2 to 0.8. And then what you see over time is, well, the first thing that happens is this sort of random, if you will, sort of unphysical initial condition. If it was a configuration of water, I wouldn't have just random values next to each other. It kind of smooths out due to the coupling, and then everything increases in value. That corresponds to the water layer getting thicker and thicker and thicker until you reach some thickness where the drop falls off and the lattice resets to 0 and it counts up again. It's thicker and thicker, then drops and drops. So the drops correspond to these flat regions here. And we sort of see the same type of behavior. There are regions that sort of are in phase, or they're growing together until they all kind of drop at once. There's a little bit of, you notice where the drop happens, there tends to be a site that goes first and it sort of unzips. If I had a layer of water under the handrail, one side drops first, it tends to pull the other neighbors along with it into a drop. Overall, there's, at least initially here, sort of a semi-periodic behavior. Yeah?
So the green represents high density water, a lot of water, right?
Purple does. So it goes, drop.
Right, okay.
Goes, drop. Yeah, sorry. I should put a sidebar on that. So the individual of the map in isolation is trivial. It just counts up and resets, counts up and resets. There's a little bit of a dependence on what that period is. It's a function of the offset and the slope. But it's easy to figure out. So in a sense, what we're seeing here is the interesting behavior seeing is almost purely due to the spatial coupling. Not so much, not dominated like with the logistic lattice in terms of local, the local site, isolated site dynamics. One of the interesting things about this system, and I'll just summarize this here, then we'll do a demonstration. So for small lattices, 5, 6, 200 or 300 sites, something like some range of hundreds or smaller, all of the initial conditions are ultimately periodic. So what we were just seeing in that space-time diagram are these sites kind of jostling for trying somehow to get into phase. And when they finally all get into phase, then the whole lattice is homogeneous. There are no spatial differences. The dynamic reduces to that of the isolated map because there's no spatial difference in it. It just kind of hops along together. The curious thing, though, if you look at how many iterations it takes to get to this periodic orbit, it grows as a double exponential. Again, this isn't obvious, it's just the result in analyzing this, which makes it, this kind of scaling behavior as a function of system size, makes it a little bit problematic to think about getting to the attractor. In the Bristol and Lorentz, that all happened very, very fast because there was a large dissipation right here. This system, imagine I had n equal 100 or 1,000. We're talking about universe lifetimes here. So we used this model a number of years ago to sort of argue this whole notion. For spatially extended systems where you have different regions sort of competing with each other to who's going to dominate, who's going to win out with the phase, that the transients can be so long, you'll never, ever practically get to an attractor. It's almost all transients. So let me show you how the system works here.
Are you saying for just the driven handrail or for these lattices?
For the logistic map, the transients typically are rather short compared to this. So what I'm saying is it's not a general result that you have these extremely long transients. It's just a question that you now have to think about. So a lot of the earliest work in dynamical systems was concerned with trying to describe fluid turbulence. A fluid is a spatially extended system, and there were these competing hypotheses about what the right mathematical framework was. So Landau comes in and says, oh, it's quasi-periodic attractor. As I'm pushing more energy through the system, the turbulent response is just more and more harmonic components. More and more quasi-periodic components, irrationally related frequencies, and so on. In the 60s, through Lorentz and some other mathematicians, like David Ruel, the idea was, no, the turbulence is actually one of these strange attractors. So a group of us ended up showing in the early 80s that it was, in fact, strange attractors that described the first stages of turbulence, what we call weak turbulence. You're not pushing too much energy through the system. But then we got kind of suspicious about the whole framework, and then sort of argued that there are regimes for spatially extended systems where the whole notion of getting to an attractor is practically irrelevant. So that's some of the background arguments for looking at this. Okay, so I went a little slow today because I wanted to finish up talking about these spatially extended systems, but maybe just make a few comments about where we're going next, because so far you've had one impression of what the course was about. That's about to change radically.